Before closing our discussion of frequency domain methods, I wanted you to take a look at a page from a book written by Nichols with two others in the 1940s, where his chart appeared for the first time. I told you that the constant contours, that is contours that correspond to various constant values in the dB gain versus phase shift plane, are not simple circles. They are curves which look somewhat like ellipses, some of them, others are open curves and so on. So, this is the so called Nichols chart that I wanted you to see. Now, let us move on. I hope by this time the expression frequency domain method is clear to you. The Nyquist criterion of stability, the method of drawing the asymptotic Bode plots, M circle, N circle, Nichols chart, compensator design using networks, all of these are based on frequency domain methods or concepts. That is, one is thinking of a sinusoidal function as a typical input function and then finding out what would be the response to that kind of an input, and therefore, one talks about gain, either absolute gain, that is ratio of output amplitude to input amplitude, or dB gain 20 log to the base 10 of the absolute gain, and phase shift or phase difference between the output and the input. Earlier to that, we had looked at the root locus method, which made use of the concept of transfer function and poles and zeros of the transfer function. There is no specific mention of any particular input like the sinusoidal input or even the unit step or the step function input, although from the control point of view, one of the things that one likes to study is the effect of disturbances, and a simple kind of disturbance which occurs very often is a sudden change from one value to another value, and this is therefore thought of as a step input or a step disturbance. But apart from that, we did not really look at any other or any specific inputs. We looked at the transfer function, the poles and the zeros as a transfer function, and then the idea of a characteristic polynomial or a characteristic equation associated with the closed loop system, its factors or therefore the roots of the characteristic polynomial and their location in the complex plane, were all the ideas that we were led to. Evans's root locus method, of course, has stability investigation as one part of it. Now, what kind of method is that? It is not a frequency domain method. It is not quite what is called a time domain method, which we will look at very soon. It may be called a transform domain, and specifically because the transform is the Laplace transform and the preferred symbol for the complex variable there is S, it may be called an S domain method. So, then we have had S domain methods. The root locus method was a particular example of that. Then we had a look at the frequency domain methods, and now we will take a look at what can be realistically called time domain methods. In a way, in control system study, the time domain methods are or should have been the most natural methods to use. Why is that so? Because the earlier control systems, going back to the time of the astronomer Airy and the problem of tracking the stars, or James Watt's governor, or the steering of ships, that is before servo mechanisms and feedback amplifiers came on the picture, the system to be controlled was described by one or more differential equations involving derivative. And so, the system description itself was, as one could put it, in the time domain. You wrote down the differential equation which involved some parameters of the system, and that is what we did for our simple motor speed control problem. Subsequently, in order to deal with the differential equation, making use of some other work or some other areas of mathematics such as the theory of the Laplace transformation, Fourier series analysis and Fourier transforms and so on, people were led to methods like the S domain method, of which the root locus method is an example, or the frequency domain method which preceded it, of which the Nyquist criterion and the Nichols chart based design are examples. In recent times, and it is not really that recent, nearly 40 years ago, investigators went back to the differential equations for several reasons. One of them is that the differential equations that led to concepts like transfer function, frequency response were linear differential equations and time invariant differential equations, or as I used an abbreviation earlier, ordinary linear differential equation with constant coefficients. The Laplace and the Fourier transform methods could be used, concepts like frequency response could be used for such differential equations only. We saw some properties of the Laplace transformation, and the first of the properties that we saw was that the Laplace transformation is linear. The Laplace transform of the sum of two functions is the sum of their Laplace transforms. The Laplace transform of a scalar multiple of a function is the same scalar multiple of the Laplace transform. And the third property of the Laplace transform, of course, concerned the derivative of a function. There is no simple theorem regarding the Laplace transform of the product of two functions. That is, if I have two functions f and g and I look at their product f times g, then there is no nice and simple expression for the Laplace transform of the product of f and g. It is possible, of course, to write an expression for the Laplace transform of f times g in terms of the Laplace transforms of f and g separately, but that is a relation which is not very convenient to exploit. Of course, for the Laplace transform of the convolution of two functions, this idea I had briefly mentioned. The convolution operation is denoted by a star usually. So, the Laplace transform of the convolution of two functions, of course, has a nice alternate expression, namely the product of the Laplace transforms of the two functions separately. But in the description of the system, the convolution operation does not occur usually. A product may occur, but not a convolution. So, the use of the Laplace transform approach was restricted to linear ordinary differential equations with constant coefficients. The Laplace transformation method cannot be used in general if the system equations are not linear. The system equations, one or more, are non-linear. That is one case where the Laplace transform method will not be applicable. Another is with regard to this part of time invariance or with constant coefficients. The Laplace transform method cannot be used if the system is not time invariant, or specifically therefore the system is time varying. This may happen because there are coefficients, what look like coefficients which multiply derivative terms, which are time varying. So, sometimes such equations are referred to as differential equations with time varying coefficients. So, if the differential equation is nonlinear, if the differential equation is time varying, or if it is both, then the Laplace transformation approach will not work. Neither will the frequency response approach work. For example, if the input to a nonlinear system, a nonlinear differential equation say, is a sinusoidal function, the output or the response of the system in general will not be sinusoidal. And therefore, you cannot talk about amplitude of the input and amplitude of the output, because although the input is sinusoidal, the output is not. So, the idea of gain is not applicable, phase shift is not applicable, which means you can't do anything more in that direction. Now, of course, it is known, or it was known, that many systems can be modeled only if you are willing to consider nonlinearity or the time varying nature of the system. That is, there are many systems, some of them have been known for a long time. By system, I do not necessarily mean a system which is a control system involved in a particular control application. I now mean here any physical system. So, nonlinearities cannot be ignored. It was known, say even 100 years ago, and at that time also people had tried to develop methods for handling systems with nonlinearities. You might remember a chapter on differential equations in your mathematics courses, where you may have looked at and solved some specific nonlinear differential equations which give rise to or gave rise to some different kinds of functions. For example, Bessel's functions, they arise when you investigate a nonlinear differential equation of a particular type. But a simple example of a nonlinear system will be a pendulum, and this of course goes back to your early college days, when one deduced the formula for the period of oscillation of a pendulum, 2 pi square root of L divided by G. That derivation made the assumption that the angle of swing of the pendulum was small. If the angle was called theta, then theta was small. And how small? Well, small meaning sin theta, which occurs in the differential equation, could be replaced by theta. So, the pendulum equation is actually nonlinear. Maybe you should write down that equation starting from first principles. Consider a general position of the pendulum at an angle theta to the vertical. Look at the forces acting on the pendulum, the force of tension and the force of gravity, and the resultant force being the force that accelerates the pendulum. And you can then write down the differential equation for the angular position theta, and you will see that it is nonlinear. So, there were physical systems as simple as a pendulum, for which it was known that the description is nonlinear. The pendulum can be described by an equation which is nonlinear, although approximations can be made. Now, after the success of the S domain and the frequency domain methods in the 40s and 50s, there arose some problems where you could not work with such approximations to nonlinear systems, or it was no longer acceptable to make those approximations. The requirements for precision had increased tremendously, and therefore interest went back to the study of differential equations. Now, in this context, first of all, let us see exactly what we mean by a nonlinear system. Now, there are two ways of defining a nonlinear system. There is one way which is a little abstract, in the sense I do not write down any particular differential equation and then say that it is linear or it is nonlinear. but rather I consider the differential equation, and as we saw for a physical system or a differential equation that describes a physical system, you have something called an input, something which you can vary, over which you have some control, and some other function or variable called the output or the response, which you do not directly manipulate or control, you do it through the system. So, one can think of a system as a relation between inputs and outputs. Very crudely we say input produces an output, or this is a response to that particular input. So, I do not even have to say that there is a differential equation there, there is some differentiation action taking place or what have you. This is sometimes referred to as a black box approach to a system. There is an input variable, there is an output variable, and there is something which has been put together such that I can change the input and I will get a change in the response. This is a very broad concept of a system. What is inside? How do I describe it? Are there resistors, motors, pipes, whatever? Of course, for a given practical situation I have to know what is inside, and that is why I said this is an abstract approach. We will concentrate only on the input and the output and the relationship between the two. Specifically, each particular input produces some definite output. With this concept of a system, one can define linearity quite easily, and in fact when we talked about the Laplace transformation and its linearity or the two properties, something exactly like this was being done. In other words, you have, let us say, an input u1 which produces a response, let us call it using control literature C1. So, u1 is the input, corresponding output is C1. Suppose we apply some other input u2, it results in a different output C2. Now, if the system is such that applying u1 plus u2 produces a response C1 plus C2, then we say that the system is additive, or we say that the system obeys or satisfies the superposition principle. So, this is one part of linearity, additivity or the superposition principle. Note that we do not apply two inputs together. What we apply is, we apply input u1, look at the response, then change the input to u2, look at the response, and then go back and apply a new input u1 plus u2, the sum of the two inputs, and see if the response looks like the sum of the original responses. The system still has one input, one output. Now, if for some choice of u1 and u2 this fails to happen, then we will say that the system is not additive, or the system does not obey the superposition principle. So, this is one part of linearity, or correspondingly one part of non-linearity. A system is additive or a system may not be additive. A system obeys the superposition principle or it may not obey the superposition principle. The second is, of course, the scaling property or homogeneity. Here what do we think of? Again, one input, let us say, one output, and of course, as some of you who will go further from this course will realize that when I say one input, I can think of several inputs as one vector input. Similarly, when I say one output, it need not be only one variable, it could be a whole set of variables being considered together. So, a vector input and a vector output, that is also possible. So, I apply input u, I get a response C, then I scale it by some factor lambda. Do I get an output which is also scaled by the same factor? If this is going to happen, then the system is homogeneous or has this scaling property. And if a system has both additivity and homogeneity, then we say that the system is linear. So, if we say that a system is nonlinear, what we mean is that one of these two properties or both of these properties do not hold. Now, this does not require you to know what is inside, although very often to find out whether a system has this property or not, you will have to know what is inside. But on the face of it, and in a very simple way, you can sort of make an assessment whether a particular physical system is, say, homogeneous by applying some input to it, observing the output, then doubling the input, seeing whether the output is doubled. If the output is not quite double of the original output, then the system does not have the homogeneity property. Similarly, you could check additivity sort of experimentally. Something has been put in a box and I have only an input and an output which I can measure and observe, and these are the things that I do with the input and output. In principle, I can find out whether the system is additive or homogeneous or linear or not. Of course, I may scale it by a factor of 2, the output may be doubled, but if I scale it by a factor of 10, I may find that the output is not 10 times. Why does this happen, or when this happens, in what cases familiar to electrical engineers can this happen? You have a magnetic field which is produced in the presence of, say, iron. A particular current produces a particular flux density. You double the current, the flux density may get doubled. But if you scale the current by a factor of 10 or 100, the flux density may not get scaled by the same factor. And so, we call this phenomenon the phenomenon of saturation. So, if a device shows saturation, then certainly it is not homogeneous. To go back to the example of the pendulum, scaling the swing of the pendulum, of course, that is not quite a system, but a large swing and a small swing, things are not necessarily the same. Now, of course, if you are not going to follow this kind of an experimental approach to find out whether a system is linear or not, and you look at the description of the system, that is what is inside, and you write down a set of equations, then how do you find out from them whether the system is linear or not? This concept of linearity is more familiar to all of us because we encountered that fairly early, in fact in school itself, when one talked about simple equations which were called linear equations or linear algebraic equations. And the simplest, of course, will be simply say the equation y equal to ax. Say x is the input, y is the output, a is simply some coefficient, a scale factor, and if this is the description of a system, and do not think that there is no system for which a description as simple as this is possible. A potentiometer or a gain coefficient implemented in some physical way is exactly of this kind. Output is just a constant multiple of the input. Now, is this linear? Is this additive? Does it have the homogeneity property? Well, from the description we can determine without much difficulty that it is so. So, let the input x1 produce the output y1, which means y1 is equal to a x1. The input x2 produces the output y2. So, y2 is equal to a x2. So, one input produces one output, another input produces another output. Think of the sum of the two inputs as being applied. So, the new input is now x1 plus x2. What is going to be the new output? The new output is a times x1 plus x2, but that is the same as ax1 plus ax2, but ax1 is y1, ax2 is y2. So, the new output is the sum of the two outputs. So, this system, or one can even say now, because this we may not think of a system, we may think of the equation itself. This equation is additive, has the property of additivity. Similarly, with regard to homogeneity, if x1 produces y1 and therefore y1 is equal to ax1, what about lambda x1? What will it produce? Well, the output will be a times lambda x1, but this can be rewritten as lambda times ax1 or equal to lambda y1. So, if the input is scaled by lambda, the output is going to be scaled by lambda. So, the system or the equation is homogeneous, and therefore, the equation is linear. this is how in fact we learned to use the word linear, or we learned to recognize equations which were said to be linear. Notice that we can talk about a system being linear and an equation being linear, and the two are not quite the same. We can take another example and see that an equation can be found out to be not linear or non-linear. Take the simple equation, say y equal to ax squared. X is the input, y is the output. Such a thing could be called a squaring device or a power law device with power law 2. And again, there can be some physical system for which this is a good model, y equal to ax square, squaring devices. Is this equation linear? Is it additive? Is it homogeneous? Now, one can quite easily verify that it is not so. For example, homogeneity. So, x1 produces y1, where y1 is therefore ax1 square. What is the output for lambda x1? Lambda x1 produces what output? Lambda x1 produces a times lambda x1 whole squared, but this is a times lambda square x1 square, or it is lambda square times y1. So, scale the input by lambda, the output is scaled not by lambda but by lambda square. So, the system is not homogeneous, or the equation is not homogeneous. Similarly, you can verify that the equation is not additive, and therefore, when we see an equation like this, y equal to ax square, having gone through this experience, we see that no, this equation is not linear, whereas the equation y equal to ax is a linear equation. So, this is how we learned to recognize, or this was our first exposure to linearity and non-linearity. Of course, a system may have two inputs, it may have two outputs, the relationship may be more complicated, but again one can, by working out, see that the system equation or description is linear or not. So, let me take an example of a system with two inputs and two outputs, and this kind of a description of course is already familiar to you. Two inputs x1 x2, two outputs y1 y2, and they are given by two equations of this kind. And as you know, one learns to write this in a more compact form, or it is not really compact, but it leads to very new ideas in the form of a matrix of coefficients. Here are the two outputs y1 y2 now put together as a single vector. So, I think of y1 and y2 as one, but with two parts y1 y2, x1 and x2 as one with two parts x1 and x2. So, here is the input, here is the output, and here is the matrix of coefficients that is involved in the relationship. Now, it is a simple exercise to find out that when the two inputs x1 and x2 are given some values and you have corresponding outputs, then you change the values given to the inputs, find out some new outputs, and then superpose them, then what happens? It is easy to verify that additivity holds, that homogeneity holds. Therefore, this set of two equations, or the input output relationship given by these two equations, is also linear. So, one linear equation, several linear equations, one recognizes it by the appearance of the equation. One need not worry about what physical system is it for which this equation is a good approximation or holds, and so on. So, linearity of the equation rather than linearity of the system, this is something also, in fact this is what one learns earlier. Linearity of a system is a more advanced and, as I said, a little more abstract concept. Now, just like linear algebraic equations, you have learnt to recognize linear differential equations. For example, the differential equation, and I am going to use the dot on the top of a variable to denote derivative. We have also seen earlier other ways of indicating a derivative. Of course, d by dt is the first method or way of denoting a derivative, but I have also introduced the symbol capital D as denoting the operation of differentiation. So, I can write down an example of a differential equation which is linear, and will verify that it is linear, although by its appearance you know that it is linear. So, let us say we have an output variable y. So, somehow in the system description its derivative appears. So, y dot equal to, let us say, a y plus b u. U is the input, y is the output. In the description a derivative of y appears, y dot equal to a y plus b u, or if you wish dy by dt equal to a y plus b u, or d acting on y, operating on y, equal to a y plus b u. So, let us say this is the description of a system. Is the system linear? Or the way we are going to find out is not by giving inputs and measuring the outputs, but by looking at the system description or equation. So, is this equation linear? How do we find out? Well, we apply exactly the same kind of test. Consider an input u1, corresponding output y1. So, since y1 is the output, what must be true? dy1 equal to a y1 plus b u1. For an input u2, suppose the output is y2, therefore, dy2 must be equal to a y2 plus b u2. So, u1, u2 are two inputs for which the corresponding outputs are y1, y2, and these two inputs and outputs satisfy these two equations. So, now we think of an input which is the sum of the two inputs. So, u1 plus u2, what is the corresponding output? Let the corresponding output be denoted by y. So, I have to find out what is this y, and I am going to ask whether this y is equal to y1 plus y2 or not. If I can show that it is y1 plus y2, then I have shown that the system or the differential equation is additive. But what equation does y satisfy? Y is the output for input u1 plus u2. Therefore, dy must be equal to a y plus b u1 plus u2, right. So, this is what I have, dy equal to a y plus b into u1 plus u2, and I have the two equations for y1 u1 and y2 u2. From that, now I have to try to find out or try to show whether y equal to y1 plus y2 or not. And you will see that there are some conditions or assumptions which I had mentioned earlier do come into the picture now. I will write down the equations for y1 and y2 below. So, I have a y1 plus b u1 and dy2 equal to a y2 plus b u2. So, these are the three equations for y1, y2 and y, inputs u1, u2 and u1 plus u2. Now, the appearance of the equation suggests that we can do the following. We can subtract from the first equation the second and the third equation. So, if I do that, I will get dy minus dy1 minus dy2, dy minus dy1 minus dy2 equals ay minus ay1 minus ay2. And what happens to u1, u2? Well, there is b u1 here, that cancels with b u1, b u2 cancels with b u2. So, there is no u1, u2 appearing in the equation. So, I have this equation, and since I am asking whether y is equal to y1 plus y2, let me call the difference between y and y2 or y1 plus y2 z. And so, I am asking the question whether z is 0 or not. Well, we almost have an equation for z. We have the equation dy minus dy1 minus dy2 on the left hand side equal to ay minus ay1 minus ay2 on the right hand side. Now, we make use of a property of the derivative operation, which in turn is a linearity or an additivity property. The derivative of the sum of two functions is the sum of their derivatives, or the derivative of the sum of three functions is the sum of their derivatives, or the derivative of the negative of a function is the negative of its derivative. The first two are examples of additivity, the third one, negative, being minus 1 times the function, is an example of homogeneity. So, here we are making use of the fact that the derivative operation is linear, and therefore, dy minus dy1 minus dy2 can be written as d of y minus y1 minus y2, and on the right hand side I have ay minus ay1 minus ay2. So, I can write this as a multiplying y minus y1 minus y2, or since I have called this z, I have dz is equal to az. So, what is this difference between y and y1 plus y2 may be, this z satisfies the equation dz equal to az. Now, from that, does it follow that z is equal to 0 for all time t? The answer is no, because we know the solution of this simple differential equation. You remember in our discussion in the beginning, we saw, or I reminded you, that a solution of this differential equation, a general solution of this differential equation involves the exponential function. So, the solution is actually zt equal to k times e raised to at, or by putting t equal to 0, we can see that zt is equal to z0 into e raised to at. So, zt is equal to z0 into e raised to at, and therefore, zt is not 0 unless z0 is 0. Now, this is something that brings us to an important consideration which we had seen earlier, reference to initial conditions. That is, when we say that this differential equation is linear, we will have to say in addition that under certain initial conditions. For example, what does it mean to say that z0 is equal to 0? Well, z0 is actually what? y0 minus y10 minus y20. So, this must be equal to 0, and one simple way in which this can be made 0 is by making all of them 0. So, in other words, now we have to say that, okay, I am going to look at the differential equation y dot equal to ay plus bu, but I will consider it only under the condition that the initial value of the response is 0, y0 equal to 0. So, under 0 initial conditions, I will study, or I will look at the differential equation. For one input, I get one response, for another input, another response. In both cases, the initial value of the response must be 0. Third input u1 plus u2, third response, again the response must be put to 0 in some way or the other. If that is done, then the system is additive, or the differential equation is additive. And of course, when you use the Laplace transform approach, one sees that more explicitly, because in the derivative property of the Laplace transform, the initial value makes its appearance. So, the differential equation is additive with this restriction. Is the differential equation homogeneous? Now, you can see that that also is going to involve this assumption of the initial value being 0. So, dy is equal to ay plus bu with input change to lambda y is the response, or let us say dy1 equal to ay1 plus bu. The response to lambda u is y. So, dy is equal to a y plus b into lambda u. Is the difference y minus lambda y1 equal to 0? If I call that difference z, then I will get the differential equation dz is equal to az once again, and this has the solution 0 only if z0 is 0. So, it means for homogeneity to hold also, the initial value of the response must be equal to 0. Of course, we saw earlier that when we did the Laplace transformation technique, that you could talk about components or parts of the response. That is, the response, although physically it is not a sum of three separate things, mathematically or in our model we can think of it as coming from three different parts or two different parts. If you remember, I talked about 0 input response and 0 state response. Response when the input is 0, but because the initial conditions are not 0, you get a non-zero response. On the other hand, the initial conditions are made 0 and input is applied, you get a component of the response. What I am talking about right now therefore is the 0 state response. Under initial conditions being made 0, the relationship between response and input is linear. Of course, one learns very quickly to recognize a linear differential equation like this as an equation which looks like this. In fact, this is how students answer the question, or for them the concept of linear is the appearance of the equation and not input output relationship. Of course, this can be extended to several differential equations involving only one input or more than one input, and this is again something which your control theory book has a lot of discussion of. For example, I may have two outputs, one input and a relationship which looks almost like what we wrote. For example, dy1 is equal to a11 y1 plus a12 y2 plus b1u, dy2 is equal to a21 y1 plus a22 y2 plus b2u, or by combining or thinking of the two y1 and y2 together as parts or components of what is called a vector, I can write this as D acting on y1 y2 equal to a matrix, again a11 a12 a21 a22 acting on y1 y2 plus b1 b2 multiplying u, or u multiplying b1 b2. Or to use a further compact notation, this can be written as dy, and one may sometimes underline y to indicate that this is not one, but this is several, like y1 y2, equal to some symbol that denotes this matrix. A fairly standard symbol is capital A multiplying the vector y plus again a symbol for the vector consisting of b1 and b2, which is multiplied or scaled by u, and therefore bu, although this u is a scalar multiple, so usually it is written in front of b, but in control literature this is a fairly standard way of writing. So, this is in fact a linear model of a system with one input with maybe two outputs in this case, or this y may consist of three components or whatever. So, again one recognizes by the appearance of the equation that the equation is linear. It is not so easy to show that something which does not look like this is in fact non-linear. For example, let me write down the differential equation y dot equal to a y square instead of y dot equal to a y, or y dot equal to a y square plus let us say b u. So, there is an input u, there is a response y, and there is this differential equation, or using the d notation dy is equal to a y square plus b u. Now, you will say this does not look like a y plus b u, therefore, it is non-linear. Now, that would not be a good answer or a really a correct answer, because I would like you to show that this is non-linear because homogeneity fails or because superposition fails. So, you have to give me an example of an input and a corresponding response, and a scaled version of the input, the response fails to be the corresponding scaled version of the output. You must either give an example, or by looking at the equations and by manipulating them, you must be able to show to me that this is the case. For example, if I choose an input y1, if I choose a response y1 corresponding to an input u1, so I have this equation, and then I talk about scaling. So, the corresponding response, let it be y equal to a y square plus b into u1 is now lambda u1. Then I have to show that y will not be equal to lambda y1. For that, I will have to manipulate these two equations somehow and show that the difference between y and lambda y1 is not 0. Now, in this case it is not too difficult, although it, as you will see, it does involve some trouble. So, going by what we did earlier, I will take this equation, and from that I will subtract lambda times the first equation, and calling the difference y minus lambda y1 equal to z, then I will get d of z equal to a y square minus a y1 square, because the u1 term disappears. And from this now I can express, let us say, y in terms of y1 and z. So, if I write this as a, y is z plus lambda y1 minus a y1 square, and so dz equal to this, of course, is squared. So, I will get dz equal to az square plus something something. Now, I have to show that this equation does not have a 0 solution, even if the initial conditions are 0. Now, that in general it is not easy to do. In other words, in general, if you write down some equation which looks nonlinear by having square terms or by having, say, sine of z and terms of this kind, the solutions of that equation are not very easy to obtain. That does not mean that the solution is not 0 or 0. So, it requires a lot more effort to show that the particular equation is linear or is not linear. What therefore you have learnt is to recognize linear equations. What is nonlinear is not simply what does not look like what is linear, unfortunately. To show that something is nonlinear, you have to do some more work and show that homogeneity does not apply or superposition principle does not apply. I will not press this point any further, but I did want to emphasize that a system being linear and nonlinear or failing to be linear is one thing, a differential equation failing to be linear is another thing. And the main point is that you can recognize something as being linear, but by its form, by its appearance, whereas there is nothing like an appearance of a nonlinear system. For example, dy equal to y square is nonlinear, dy equal to y cube is also nonlinear, but that is not all. Dy equal to sin y is also nonlinear, and so on. So, in other words, there is nothing like a general nonlinear model, whereas there is something like a general first order linear differential equation model. The model that I have written earlier, dy equal to ay plus bu, is a very general first order linear differential equation model. And this is the reason why nonlinear systems are very difficult to study, because there is no particular form that all of them have, whereas all first order linear differential equations by their very choice have a particular form. That is why we recognize them as linear, and therefore they can all be studied together. Nonlinear systems, unfortunately, cannot be all studied together. So, there is no general statement that I can make about all nonlinear systems, whereas I can say something about all linear systems described by a first order differential equation. This is why the study of nonlinear systems has proceeded more slowly, has been very difficult, and therefore the S domain and the frequency domain methods were applied to linear systems and were developed quite well before people went back to the study of nonlinear systems.